Hello everyone, I am sure you are having good time. Welcome you once again to MSP lecture series on interpretative spectroscopy. In my previous lecture I discussed about first order spin system, taking several examples, and one such example I considered was styrene. In styrene, although it was appearing like a first order spectrum, it's not first order spectrum. So that means germinal coupling we came across, although magnitude was about 1.4 or so. So how that happens and how to interpret, let us look into now second order spin system. Second order coupling we call it as. So the examples of 1H NMR spectra we discussed so far involved first order coupling. So that means the chemical shift difference, we call it as delta delta, between the nuclei is considerably greater than the coupling constant, usually 5 times greater. That means delta delta is greater than J, then it is called first order coupling. When delta J is larger, the nuclei involved in the spectrum are designated with letters from extreme ends of alphabet. That means, for example, A and X, AMX, AX2, A2X2, depending upon how many such nuclei are there in a given molecule. That means when delta is larger, the nuclei involved in the spectrum are designated with letters extreme ends of alphabet, that taken from extreme ends of the alphabet. AX we come across, AMX, AX2, A2X2, etc. So when delta J is less than 5J, that means chemical shift difference is much smaller than coupling constant, then for such a system we are using letters close together in the alphabet, for example AB, ABC, A2BC, something like that. So in those cases what happens, the Larmor frequencies of nuclei of different elements are always very large. In those cases, in the first order spectrum, if you consider, or in first order coupling, the Larmor frequencies of nuclei of different elements are always very large. Second order coupling can occur only between the nuclei of the same isotope. One should remember that one. Nuclei of the same isotope only can exhibit second order coupling. Okay, for example, as I said, protons on same carbon atom, when it is there and they are chemically equivalent and magnetically non-equivalent, in that case we come across, but vicinally substituted fluorine and hydrogen. So that can never be second order coupling, that is always first order spectrum. That means second order coupling can occur only between the nuclei of the same isotope. Example, between two 1H nuclei, 3 19F or 3 phosphorus. Since the chemical shift differences are very small for 1H, the majority of second order couplings are observed in 1H NMR spectrum. Here surrounding hydrogen we have only one s electron and it is spherically symmetrical, and hence chemical shifts are very small range, we have 1 to 10. Only in exceptional cases where we have coordination compounds and metal to hydrogen bond is there, in that case we may come across up to 60 Hertz, 60 ppm. Otherwise in most of the organic molecules it does not go beyond 10 ppm. So that means as a result what happens, since the chemical shift differences are very small in 1H, the majority of second order couplings are observed only in 1H NMR spectra, and we also come across in case of phosphorus NMR also. So let us consider a simple second order spectrum such as AB. Since the chemical shifts of the nuclei in a second order system are similar, the energy levels are much closer compared to the same in the first order. This is very, very important when we differentiate between first order coupling and second order coupling. The chemical shifts of the nuclei in a second order system are very similar. That means they have chemical shifts much closer. The energy levels are much closer compared to the same in first order spectrum or first order spectrum. So let us now, I have given a series of spectra here. They represent typically AB case. In AB case, the middle energy levels are similar to A2 here. If you see here, they are A2. As these middle levels becomes closer, it becomes difficult to tell which nucleus has which Mi value. That is the problem we come across in second order splitting. As these mid order levels becomes closer, it becomes difficult to tell which nucleus has which Mi value, whether it has plus half or minus half. Similar to A2 case, consider the linear combination of two-way functions here. Since these new functions are mixtures, it is no longer possible to designate the transitions whether they are due to change in Mi of A or B. As a result, by simply looking into spectrum, it is no longer possible to determine the chemical shifts of A and B. So, general patterns of the AB spectrum depends on delta A of A and that of B and the corresponding J value. So, to what extent delta J is comparable, delta is comparable with delta J, that would tell you the separation. The spectra shown here are for J equals 10 and a variety of delta values. So here in all of them, if you just look into it, coupling constant is kept 10 and then a different variety of delta values are given. When delta is very large relative to J, spectrum appears as a distorted doublet. The intensity of inner lines increases as J by delta increases here. So that means at delta equals 0, the spectrum is reduced to a single line as in case of A2 system. So this is how you can correlate, and also all these cases are of different AB depending upon the difference in delta with respect to J value. Few points to remember in case of second order coupling is, in a first order spin system, delta must be greater than delta J. That means what one should remember is this one is much greater than delta J, not delta J. All chemically equivalent nuclei must also be magnetically equivalent. Okay, this is very important. In first order spectrum, all chemically equivalent nuclei also magnetically equivalent. That means if you are considering two geminal hydrogen atoms, so they are chemically equivalent as well as magnetically equivalent. What is the meaning of chemically equivalent and magnetically equivalent? Two or more nuclei are chemically equivalent if they can be interchanged by the operation of some symmetry elements of the molecule. So two or more nuclei are chemically equivalent if they can be interchanged by the operation of some symmetry elements of the molecule. For example, let us say you take phenol, and we have ortho hydrogen atoms are there, and simply by doing a C2 rotation with respect to OH and para hydrogen atom by rotating, okay, what happens? If we cannot distinguish them, then we can say both are chemically equivalent. In case of AB system, we are giving this delta AB equals delta 1 minus delta 4 into delta 2 minus delta 3, and the middle point will be given as delta usually, and then J can be calculated delta 1 minus delta 2, or that is nothing but equal to delta 3 minus delta 4. This is how the J is determined here, and also chemical shift also determined here. Delta AB equals, we have to take the middle of this one. Now let us consider some examples here. As I mentioned, if you consider here chlorobenzene, and if you consider this as a rotational axis, and if you do C2 rotation, and 1 and 5 cannot be distinguished, are indistinguishable. Similarly, H4 and H2 are indistinguishable. These two are called chemically equivalent, and these two are called chemically equivalent. And again, if you take in this one, all these are chemically equivalent here. And then again, if you consider here, again they are chemically equivalent here because you cannot distinguish them. And similarly, if you consider this picture I have shown here, H on C2 and C4. So this one and whatever the hydrogens we have on C2 and C4 I haven't shown here, or cis2 CH3 and are equivalent, so as H on C2 and C4 trans to CH3 plane. So plane extending through C1 and C3 makes C2 and C4 equivalent. And similarly, if you look into Fe to CO9 here, the axis through Fe bond, if you make it, terminal and bridging are equivalent, these three are equivalent, and these three are equivalent. So these are equivalent and these are equivalent. So this is how we can identify whether some symmetry operations can make them indistinguishable after that symmetry operation. So that means now we can have a better understanding of chemical and magnetical equivalents or non-equivalents. So if you say chemically and magnetically equivalent nuclei, that means magnetically equivalent means each member of a chemically equivalent set of nuclei must be equally coupled to each member of any other chemically equivalent set in the spin system. So that means here in chlorobenzene, if you consider H1 and H5 are equivalent so as H2 and H4. So these two are identical, these two are identical equivalent, and the third set is H3. Is H1 coupled to H2? Okay, H1 coupled to H2 is same as H5 coupled to H2. Answer is no, because of the distance. That means if each member of one equivalent set is not equally coupled to each member of second set, it cannot be first order. So this is how you can determine whether a given molecule would give a first order coupling or second order coupling when you have situation like this. If H1 we are considering, the H1 interaction of H1 in H2 is different from H5 and H2. Similarly, H2 interaction with H1 is different from H2 interaction with H5, or we can consider H4 interaction with H5 is different from H4 interaction with H1. So in this case what happens? It cannot be first order. So chlorobenzene is an example of three spin systems. If you designate this as A, this is A prime, and B, B prime, and C. So we call it as this one. And then A prime, what we say is the one nuclei with prime says that they are not magnetically equivalent. A and A prime are chemically equivalent, but they are not magnetically equivalent. And similarly, B and B prime are chemically equivalent, but they are not magnetically. So the prime A here represents chemically equivalent but not magnetically. So letters in the same region or nearby alphabet indicate the similarity in their chemical shifts. That's the reason when we take AA, BB and C, that means they have almost very similar chemical shift values. If the chemical shifts of H1 and H5 are significantly different from that of H2 and H5, then the spin system would be A, BB prime and XX prime. That can happen if the magnetic field strength is much larger, as delta would be larger. So this is where the significance of going from low field NMR instruments to high field NMR happens. So when you go for higher and higher instrument, what happens? If you take chemical shift in hertz, the separation will be much larger. As a result, what would happen? The all complicated second order spectrum can be converted into very simple first order spectrum. This is where people always look for 400, 500, 600 megahertz instruments instead of using 200 or 300 or even 100 megahertz instruments. The moment we designate with prime, A prime, BB prime and C, that means A and A prime are chemically equivalent, but they are not magnetically. That one should remember. And that one can understand by simple analogy, whatever I shown here. And ideal example is chlorobenzene. So remember that one. So now let us look into three spin order system. For calculating spin multiplicity or the number of lines in a peak, 2ni plus 1 is not useful for second order spectrum and it only for the first order spectrum. Again, using 2ni plus 1 rule, where n is number of identical or equivalent nuclei and I is the nuclear spin, this one holds good along with the corresponding Pascal triangle only in case of first order spectrum, but in the second order spectrum we cannot use this rule at all. So now let us consider a 19F NMR spectrum of this molecule here, trifluoroethylene, and this is an example of AMX spin system consists of three sets of doublets here. Is a 19F NMR we are considering, and 19F also is 100% abundant and I equals 19F. If you consider I equals half and 100% abundance is there, so it's as easy as 1H, or it's very similar to 1H NMR or 31P NMR. So now if you just look into FA, we have doublet of doublet, FM we have doublet of doublet, and FX we have doublet of doublet is there, and corresponding coupling is given, and MX and MX coupling is there, and AM coupling is there, and MX coupling is larger, again trans coupling is there, and then next AM coupling is there, and that is 56 hertz, and AX coupling is there, that is 76 hertz. So you can see here, this appears like a first order spectrum. So when two of the three nuclei have similar chemical shifts, I am repeating again, when two of the three nuclei have similar chemical shifts, the spin system is designated as ABX. When two of the three nuclei have similar chemical, we have three nuclei are there and two of them have very similar chemical shifts. In that case, the system should be, spin system should be called as or designated as ABX, in which the relative sign of the coupling constants affect the appearance of the spectrum. So AB portion consists of 8 lines that resembles two sets of quadrates, often they are overlapped. So AB portion itself will be consisting of 8 lines that resemble two sets of quadrates, and often they are overlapped and giving a different type of intensities for lines. And the X portion consists of 6 lines with 2 lines being very weak and almost they are in the baseline. Transition from AMX to ABX is shown in the next spectrum I am going to show here. So you can see here how AMX spectrum, where it appears like a first order spectrum, is converted into a second order spectrum because of the very little difference in the chemical shifts of A and M. So here and here. So now let's look into a few points I have listed here. These series of spectra, what I have shown from 1 to 4, represent transition of a first order spectrum AMX to ABX and eventually to A to X. So now these are all simulated spectra. AMX with respective chemical shifts of 4, 2 and 1.1 ppm, where JAM coupling is 12 and then JAX coupling is 3 and JMX coupling is 10 hertz. Next, in the second one, this is about the first one I told you. In the second one, again this ABX system with respective chemical shifts of same 4, 3.6 and 0.1 ppm, and JAB value is brought down to 9 and then BX is 3 and AX is 7 here. So now spectrum 3 represents ABX system with AB chemical shifts of 4, X of 0.1, here only 1 and 0.1 ppm, and the coupling constants are same as that we saw in case of 2, 9, 3 and 7 hertz. Now in the A to X system here, what happens? With A chemical shift of 4 here, and then this is 0.1 and then JX is only shown, that is about 9 hertz. So sometime you can see some of these variations are there, and as I said, these values depends on the chemical shift difference between A and M. And as the chemical shifts of X nuclei moves closer to those of A and B, it becomes ABC system. Eventually now we saw M moving very close towards A to become AB. In the same fashion, if the signal due to X also starts moving towards B, it becomes a ABC system. Spectrum can have up to 15 lines here. You can see here, this is a typical ABC spectrum here. ABC spin system, I have given 2 here, one at 100 megahertz. The chemical shift values for ABC are 4, 3.7 and 3.4 for A, B and C, and the corresponding coupling constants of AB is 9 hertz, BC 3 hertz and then AC 7 hertz, and the same coupling constants are kept, and the spectrum recorded at 300 megahertz would be something like this. Here you can see clearly as the field strength increases, they are moving away from each other. When they are moving away from each other, and for example, if you go for maybe 400 or 500 megahertz, they will move even farther apart, and then it becomes simple AMX system. So this is the advantage of recording spectra at higher magnetic field strength. Let us consider another simulated spectrum with ABX spin system. Here you can see here ABX spin system is there, and delta A minus delta B equals 10 hertz here, and then delta AB equals 10 hertz. And since we do not know the sign, always if the sign is not known, always we represent the magnitude, but we are not mentioning the sign. And when we look into the sign here, so when we are ignoring the sign, it is always ideal to represent in modulus. So this one is -4 and this is 1 hertz. So that means basically if you consider this ABX spin system, X resonance resembles a doublet expected for a first order spectrum here, with X only coupled to B. Only X, ABX, only X is coupled to B. Close examination of expanded version actually shows 6 lines for X. This one shows 6 lines, and it is not first order. In such cases where resonance appears to be not affected by another nucleus, HA or XA are said to be virtually coupled. So that means this a typical system where we have this kind of coupling values and chemical shifts, we come across virtual coupling. Let me stop here and continue more discussion on second order system in my next lecture. Until then, have an excellent time.